So one of the reasons, major reasons for inviting Kevin here today is to present him with our 2026 Distinguished Alumni Award. We're just extremely proud that he's a graduate of this program. It's awarded to Dr. Kevin Furlong in recognition of his seminal contributions in global tectonics and geodynamic processes. So, Kevin, congratulations.
Well, thank you very much. I hope they will let me take this on the plane. Is this a weapon?
If not, we can certainly mail it.
No, I totally no problem. Well, thank you all very much. And I mean, I have to say, you know, coming to Utah was the best decision I made. I can't say I made it for only the science. I did spend the winter before here in Jackson, Wyoming as a ski bum. So, you know, where can you merge academics and ski bumming but Salt Lake City? So, but it turned out to be the best thing I ever did. And I really I would argue I owe my career to this department. So I really am so happy to be back and really proud to be part of this department. It's great to be back. I really enjoy coming back. And I think the last time I was here sort of visiting the department was 14 years ago. I think 2012. They had a seminar in this room when Dave was retiring. And then I've been back and forth when I've been in Salt Lake, just stopping in, but this is really great to come back and meet a lot of new people, catch up with some of the other ones. There are still a few people in the room that were my mentors when I was here. So, you know, but it was a great time. And before I talk about the San Andreas, I do want to just say a couple of things. Okay, so as I mentioned, I worked with Dave Chapman, and I want to thank the Department of Geology and Geophysics for inviting me in the award. Also thank the university, a great time. I arrived, I think, at a great time here. It was a period of growth in the department. A lot of new people were hired. It was really exciting to be around with a lot of new people. And I think many of you are experiencing that now also, as a new generation has been coming into the department, and it makes for a lot of excitement. And I worked with Dave Chapman. I came here actually just to work in geophysics. Maybe in seismology was unclear. I'd done math and geology as an undergrad, so okay, you do geophysics. Dave arrived the same, actually I preceded him here by a few months. I arrived in the summer and we caught up, and about halfway through my first year, I started working with him. And it's been great. I mean, it was a wonderful time, and it really worked out quite well. Just for those of you who know Dave, you will recognize these settings. Those of you who don't, the left-hand side, this was up in Alta at his official retirement. He didn't actually retire then, but that's the way people are. This was, we had a skiing holiday after the seminar series here. He's with his brother, Tony, who's a Tibetan Lama, and worked very closely with the Dalai Lama and those groups. But it was a beautiful sunny day in April 2012. But I think more importantly, this shows Dave acting as the dean of the graduate school. At a conference we had up at the Fort Douglas, he was making sure the grounds of the university were kept neat and clean. But you know, he just picked up the bag and went around and collected all of our luncheon gear. So, back to the San Andreas. So we all, I mean, this could be a really short talk. Everyone in the room, if they've taken an introductory geology course, has learned about the San Andreas. It's this big fault in California. It's, you know, they make movies about it. They do all sorts of things. And there is sort of an official San Andreas fault. You know, there's fault things, but it's really interesting is the official fault was defined in 1908 in the Lawson Report, which was done after the 1906 San Francisco earthquake. And it was based on essentially Lawson, who was an engineering professor at Berkeley, had a team of people. They started out here. He sent one team on horseback to the south, one team on horseback to the north, looking for evidence of the earthquake. And so they mapped out the fault. And so essentially, they mapped out a fault from here at Point Arena down to somewhere around here near Hollister, California. And they called it the San Andreas because it went through the San Andreas Lakes on the San Francisco Peninsula. And then they continued it down through a very prominent geomorphic feature to the south. So that's what we call the San Andreas. And that's the map that they made in 1906. Since that time, this has been cast in stone. And as I'll show you, some parts that may not make a lot of sense, but also it's a fault on the surface that had an earthquake in 1906. That's what's being mapped here, not necessarily the large-scale plate tectonic boundary of Pacific and North America. And we have to distinguish between those two. And if we just looked at present-day earthquakes, that's a map on the right, the thing that's identified here is the San Andreas is basically has no events on it. So in the last 30 years, with the exception of a cluster of events down here in the Loma Prieta earthquake, there's been no action on that thing, but there's been lots of action on faults in California. So we have to be a little careful about putting too much emphasis on 1906. It's important, a big earthquake, but it's not all that's going on there. And so we want to worry about a variety of questions. So as we'll see, it's a work in progress. The building of the San Andreas Fault is a work in progress. And there are a series of questions that has us think about. It's presently forming in the north, what we call the Mendocino Triple Junction, near Eureka, California, Cape Mendocino. North of that, we have subduction, the famous Cascadia subduction zone. And south of that, we have the San Andreas Plate Boundary that takes on different names in different places on different faults. Seismicity is very complicated in the area. Lots of earthquake activity right up at the transition. No earthquake activity just south of that. And then it builds up toward Central California, and we have a lot. So we have a bunch of questions we want to think out. Like, what is the plate boundary? Where is it? I mean, so it should be a first order question. Major plate boundaries, we want to draw them on a map. But how do we draw them on the map, and where should we draw this one? And we need to also make sure we distinguish between a fault strand and what actually is happening on a larger lithospheric plate tectonic scale. What controls that location? And how does that history of where it formed, how it formed, when it formed, affect its behavior today? If you live in California, earthquake hazards are a big issue. And the question is, does it matter how this fault formed? It formed, the Wasatch Fault, big concern here, totally different type of history. It may affect its seismogenic characteristics quite a bit. And the interesting thing about the San Andreas, in a sense, is that this was a plate boundary that our understanding of it has developed in sync with the development of plate tectonics. It's one of these things that it wasn't really recognized to be fundamentally important prior to plate tectonics. Tanya Atwater's work, as I'll mention in a minute, was fundamental in making it clear that it did. But it also means that it's a work in progress, our understanding of it. So what we thought we understood 35, 45, 50 years ago, what most of you saw in the introductory textbooks has been superseded or improved upon or added to by work that's done since that time. Let's see, So to start out, this fundamental, if you haven't read Tanya Atwater's 1970 paper, GSA Bulletin, you should. It is truly amazing. This was a chapter of her PhD thesis, and what she was able to figure out with data sets that people today wouldn't even consider, and it's basically virtually 100% correct. and it's held up since 1970. So 55 years, and it still is sort of, every part of it is correct, the things that she saw. But she was the one who recognized that this was an ongoing feature, that it developed because of plate interactions, and that the San Andreas Fault keeps growing and the plate boundary keeps growing to the north at the expense of the Cascadia subduction zone. A few years after that, Bill Dickinson and colleagues were working on sort of trying to put the geology into the plate tectonics, and he recognized that the way it formed, there would be a large-scale gap, of what was termed a slab window, where there used to be subduction and now there wasn't. And so that's going to change the playing field. You're going to have mantle perhaps come into the area, causing heating, but also bringing different chemistry to bear. You're going to have this grow through time, and this may have huge impact on the whole development of the Western North America since 20 million years ago. So that's now been built upon. We got involved. Actually, this is a paper that was written in the building next door. George Zant was here as a postdoc at the time. He had just done the first tomography, local tomography, seismic tomography of a region, and he found this weird low velocity layer in the uppermost mantle lower crust just to the east of the faults in central and northern California. And I was working on thermal modeling, subduction zones, et cetera. So we got together and we put together this model of how the slab window would produce the observations, the heat flow, the elevation, the volcanism that was developed in that area. And so we published this in 1982 in sort of concert with Dickinson. We both had presented our stuff, both Dickinson's group and George and I, at the same AGU meeting. They were a little faster at getting things published, maybe connections, I don't know. But we assumed a couple of things. We assumed we knew something about the crust of California, which we didn't, that it was common, and we assumed that we didn't have the data to say what the three-dimensional details were. So we were agnostic on that, but we came up with this slab window model that we built on. And that took off, and people were talking about the slab window, and everyone was following it, and lots of little things were going on. And then, like any good idea, there's problems with it. And people started noticing the problems. And the problem, the biggest problem, was as part of this, I was part of a major seismic experiment, and what we called an onshore-offshore seismic experiment, where we put seismic instruments on different arrays on land. We had ships offshore that were setting off air gun blasts and explosives on land and all that to try to map the geometry, the structure of the crust. And the goal of that was to look specifically at the southern edge of the Gorda slab, see where the slab, the subduction slab was. So we had lines north of where we thought it was, south of it, and a whole series of these things. The experiment was designed knowing that the crust was 25 kilometers thick. So the station spacing was designed for that. We could do classic seismic refraction type, wide angle reflection type work. We run the experiment and we can't see the bottom of the crust. The crust is thicker than 25 kilometers because it is. And the seismic waves were bouncing off of a deeper moho. Now, with some further refinement, that was able to be teased out of the data. But at the same time, myself, Harley Benz, Antonio Villasenor put together a updated tomography model of the region. That's this, and here's the profile here. This is what the active source people saw. They saw a moho here, a moho over here, and just crust. And then they lost resolution. Well, we saw the same picture, moho, moho, but we could follow it down through here, and it got to be quite thick, like 35 to 40 kilometers thick, right where the transition is occurring. So that was sort of a problem. the crustal structure wasn't constant in thickness. Now, this could be just a serendipity. We just happened to be a special place where it just happened that the transition from subduction to San Andreas happened to be where the crust was thick, or maybe it was telling us something about a process. Well, we looked at some other details of that, and one thing was the volcanism. There's an interesting set of volcanics that are called the Coast Range volcanics because they erupt in the Coast Range of California. They're young. The oldest one is like 12, 13 million years old, 15 million years old down in the south. And they erupt after the triple junction goes by. So they erupt after subduction has ceased in the area, and we now have this other area. Now, we initially interpreted those to be associated with the upwelling mantle into the slab window. And we had to come up at high temperature, 1200 degrees, like mantle should be. And we've published a series of papers dealing with that, myself and Mian Liu and some others. And the timing of them, the most recent one is one at the active volcanics at Clear Lake in Northern California, about 2 to 3 million years after the triple junction goes by. Okay, and we presented this, and I was at a conference, and Chip Lesher at UC Davis says, you know, I really like your slab window story, but I've been having a group of our students in our petrology class take samples of these Coast Range volcanics. He's over in Davis, and they are not hot. They're not high temperature melts. They're probably pretty wet. They're probably pretty low temperature as these things go. So it doesn't fit your model of high temperatures. He said, does that matter? And it's like, well, yeah, because that's the way we figured out the heat flow and all these other things. So with his help, had a student who went out, Jamie Whitlock, she sampled all of the volcanoes, got the andesites, basaltic andesites, things like that. In his lab, we were able to analyze the chemistry of them. And so, you know, the question we wanted to ask is, when we formed the slab window, where did the melt generate from? Was it from mantle that came from the mantle wedge, the old subducted zone mantle wedge, or was it from sublithospheric upper mantle? So the stuff that might be like you'd see at a mid-ocean ridge. So the assumption was the chemistry of these rocks, we had two end members. The Cascade arc, that's the arc signature on the top figure, or a Morb signature. So Jamie does the analysis, and they all were perfect fingerprint match to the Cascade volcanics. So the source area of the Coast Range volcanics is the same as the source area of the Cascade arc, i.e. the mantle wedge, which makes it lower temperature, wet, and it then melted because it flowed in to fill the gap as the slab is removed. So that was sort of the story, but now we have to say, okay, but if we try to run our models with a lower temperature mantle and all this, it doesn't work. So, you know, the question becomes, how do we resolve that? Well, long nights drinking beer somewhere, perhaps, we came up with what we termed the Mendocino crustal conveyor. And actually, this was, you know, as a way science works. So I'd been thinking about this, and Rob Govers had finished a postdoc with me. He was back in Utrecht in the Netherlands doing numerical modeling. And we were talking about and I said, you know, here's this idea. Could it be this? He said, yeah. So literally booked a ticket, flew over for a long weekend. We spent the weekend running models, you know, middle of the semester, and it worked. We had an explanation to produce the observations, the geological, geophysical observations that we previously had been attributing to high temperature mantle. We now could do by a deformational mechanism associated with the migration of the triple junction. Essentially, the bottom line of it is that as you have a slab window, you will get hot mantle come into this area. It will cool rapidly against the base of North America and against the edge of the subducting slab, both of which are cold. It will become very viscous, and you'll get a viscous coupling between the two. So as the Gorda Plate, as Cascadia continues to move to the north, it drags this coupled mantle with it, which drags the base of North America, and you have this ductile thickening. So it's purely theoretical. Luckily, the reviewer of this, Harvey Kelsey, when we sent it to Geology, why am I reviewing one of Furlong's papers? But then he also said, wow, they're predicting this pattern of uplift that we see in the river reversal patterns of Northern California. He had a student who was mapping the drainage reversals in the coast ranges of Northern California. Now that's, of course, the review you want to get, right? The reviewer sends, the authors don't know this, but they have actually provided the explanation for all of these geological things we see. So it was accepted. And Harvey and I have continued to work on this problem since that time. But in this model, basically it's a numerical model. We did a variety of things, but we could produce patterns of crustal thickening. That would then, we could use that to say things like where the strain would be, uplift, and there's several things going on. You had both sort of what we might call the isostatic uplift due to crustal thickening, but there was also sort of a dynamic or a mechanical uplift in subsidence due to the deformation of the system, the bending of the plates and stuff. And so a very complicated pattern of uplift subsidence that was observed with the river drainage reversals and things like that could be explained by this model that we had. And so we had a model, and what made it useful was not it itself, but that it made predictions that could be tested by a variety of observations, which is really, as a modeler, what our role, I think, is and should be. It's not solving the problem, it's helping to figure out what are the consequences of a particular process and use observations of various sorts to then constrain it. And so we could test it, and lots of different people tested it, and it's held up since that time now for essentially 25 years. One of the really interesting things that came out of it was Northern California has an interesting shape to it. There's Cape Mendocino, nose sticking out. But when you look at the basins within the coast ranges of Northern California, some of them are marine basins, some of them are terrigenous basins, some of them are fluvial, some of them are marine. And they're different ages and things. And Harvey Kelsey had put together a sort of a database of this as he worked around in the area. And what we saw was if we plotted north to south on this axis, and then age of the basins, the sediments in the basins, or the deposition in the basins, on that same plot, we saw a very interesting pattern that, depending on where we were, if we were in the north, basically everything was marine. As we went further south, we would have things that went from being marine, reading down, because old would be at the top. They went from being marine to being continental, right as the triple junction went by. So it sort of was saying that this uplift subsidence pattern that we were predicting in the local transition was actually preserved in the landscape in the development of this sequence of basins. And that allowed us also to define the coastal geometry, the coastal geography going back in time. And so we could actually say, okay, 6 million years ago, this is what the coast of California looked like. All of these areas here would have been below sea level. They're still North America, but they were, but then with crustal thickening and these other processes, they were uplifted. So we ended up saying, okay, in the whatever period of time, that's 1990, that's 1980s, or 2000, So in that 20-year period, we went from a simple model, which in some sense, yeah, it captured some aspects of the problem. It appeared to sort of match some of the data, but with assumptions that we now know not to be appropriate. And that led us then to a series of advancements that brought us to what we call the MCC model, which now is compatible with a large or range of things, the petrology, the crustal structure, the rates of surface processes. Josh Roaring at Oregon has applied this to the landsliding history and stuff, and it all seems to make sense. And it also, by having the details of how the crust thickens and thins, it also can fit the heat flow data quite well. And we'll get back to the heat flow data in a bit. So over that period of time, till about 20 years ago, 2006, we made a bunch of advances of how the San Andreas formed, perhaps. We validated sort of it forms in the slab window. The variations we see are more than just passive North America changing from being subduction under it to not subduction under it. There's a lot of stuff happening to North America during that time. And still the question, 2006, was why is the fault structures where they are? You know, why aren't they just on the edge, the thinnest part of North America or something like that? So that brings us sort of to the main part of the talk. So since 2006, what's happened? Smarter people have come along. But more importantly, a lot of new data. We now have a dense GPS network throughout the region. So we can monitor, you know, really high quality crustal displacement data. Crucial to this. We have much better seismic imaging of the region, and I'll show some examples of that because of things like EarthScope. Lots more seismometers went out, lots of more things, more modeling approaches have been done. And there's also 20 more years of earthquake data. And in Northern California, the data are really good in terms of locations and things like that, partly because they have a station like every 50 meters, it seems. I think it's like Starbucks. You have to legally be able to see from one to the next, or else they need to fill in the gaps. But this very dense, high-quality network makes a huge difference. So we want to ask and answer these three questions. First one, which is still there, where is the plate boundary? You know, it's nice to say, well, it's in the slab window. But where actually is it? And why does it form where it does? And the details of that. So we'll look at that. And first, let's look at where the plate boundary is. Now, as I said, we have a really good geodetic network now in Northern California. Probably as good as anywhere in the world except maybe Honshu, Japan. They, after the Kobe earthquake, went into overdrive, and I think they have probably double the spacing that we have for GPS in California, but it's really good. So we have, you know, each of those arrows represents a station that's been recording data for 15, 20 years. We also have a good thing that they don't have in Japan. We've not had any earthquakes in this area, which means that the signal being recorded by the GPS over the last 20 years or so is purely sort of the plate tectonic motions, the creep, things like that. None of it is major earthquakes and all of the other time-dependent things that happen after major earthquakes. So we can do a very simple approach to this. We can treat it as the standard model that's done in these fault geodesy type things of a elastic layer over a half space with a dislocation in it, a ductile shear zone, which would be the deeper part of the shear zone. And there's pretty simple math for this that points out what it would look like. And if we go through it, you get this so-called arctangent function, which is what you get for a locked fault, a non-slipping fault in the shallow, overlying a creeping or a continuously moving shear structure at depth. And the shape of the function tells us something about the depth of the lock zone. And the amplitude of it tells us about the relative motion on either side of the structure. So if we think of this on a lithospheric scale, since we haven't had any big earthquakes, the GPS is recording the motion of the sub-upper crust shear zone, the part that isn't seismogenic, the part that is ductile. And so if we look at that data, so here are the data. If we project it all onto a single sort of west to east profile, we get that. I mean, it's as good an arctan as I've seen in nature, and we can fit it, and it says that the locking depth of the fault would be about 20 to 25 kilometers, and the velocity across it would be about 40 millimeters a year. Well, the 40 millimeters a year fits with the plate motions. The total plate motion is about 50 millimeters a year, but about 10 millimeters per year of that is taken up in the Eastern California shear zone on the other side of the Sierras, in Long Valley and Owens Valley in that area. And the 25 kilometers is sort of compatible with the depth of earthquakes, the locking depth that we'd expect for earthquakes. That's a little soft because the width of the shear zone at depth will affect that apparent locking depth. If the shear zone is very narrow, it will appear to be shallower than if it's very wide and things like that. But for our purposes, this seems to make a lot of sense. We can then take that and we can project it onto California at every, and what we see is that the plate boundary from San Francisco south, it runs right along the San Andreas fault, the thing we call the San Andreas. But when we get to, this is sort of Hollister, San Juan Bautista, there the plate boundary continues right up along the Calaveras, Hayward, Rogers Creek, Makama faults. And the San Andreas itself is just sort of an also-ran. So that's what's happening at 30 kilometers, 50 kilometers, 70 kilometers depth. The faults are what's happening at 10 kilometers depth. So we have this dichotomy. We have two different parts to the plate boundary. We have the faults, that we have a bunch of faults, and then we have a single, relatively localized boundary. And interestingly, this boundary exists, we see it geodetically north of where we see any faults and north of where we see any earthquakes. So it's sort of this ductile thing going on. So we're making the San Andreas boundary. I think we've made some progress. This used to be a lake, Lake Pillsbury, but California's had this drought thing. And so now it's an elk refuge unintentionally. But where is the San Andreas Plate boundary? Well, it's inboard of the western edge of North America. It's in the slab window area. There's a bunch of faults that lie above it. In the south, they're the ones that we've thought of as being the main faults. But in Northern California, there are actually a bunch of other fault strands. They all have different names. But if you remember back to that picture of where all the earthquakes are, all the little earthquakes, they're on those faults. So the present day, if we were plopped down on Earth today and said, what are the earthquakes like in California? Here's the boundary. We wouldn't be wrong because we would draw it through the earthquakes, and that's where the boundary is. It's just those are not 1906. They aren't maybe necessarily always the biggest one. So we still have to know why it forms and where it does. And that gets us back to sort of the Atwater story. She put this story together. As I said, read the paper if you haven't. It's very readable. And she noticed that when the East Pacific Rise interacted with North America, there was going to be this pattern of fault and seizure and development, and that would form this San Andreas Fault. Now, there is a little bit of serendipity here. It happens that the motion of the Pacific Plate is near parallel to the western margin of North America. If it had been different, the boundary wouldn't necessarily have been a strike-slip fault. It could have been a rift zone if it would have been a little bit divergent. If it had been more convergent, it may have been a oblique convergent zone. But for whatever reason, it formed the way it did. And so the fault then forms in that sort of regime. And again, this picture we had, we get the slab window, but where the fault is, we didn't really know. So we have to go back and think a little bit more about why it formed where it did. So we know why it forms. The plate tectonics of the mid-ocean ridge interacting caused the Furlong plate to sort of cease existing, and it got replaced by the Pacific, which was moving in a different direction. And that led to this strike slip. But we don't really have the issue of why it handled where it is. And this is a huge trench that was done in Northern California on the Makama system. It's a very interesting fault. It creeps at about 6 or 8 millimeters a year, but it also has big earthquakes on it, apparently, based on the trenching. So, creeping is not enough. This was done, they were building a new hospital, and they had to make sure the hospital was not on the fault itself. So the hospital is 50 meters from the fault. According to the laws in California, that makes it fine. But we do want to say, this is really our main question as, what caused it to form, where it did, and how does that play out? And we'll see that plays a big role. And that if we zoom in on Atwater's model of what went on 28 million years ago, we see that the Mendocino Fault, the thing that we think of as being the boundary between the whole system, it wasn't the first thing to run into North America. There's this thing called the Pioneer Fault, Pioneer Fracture Zone off of Central California. It hit first, and so initially, we would have had a Pioneer triple junction instead of a Mendocino triple junction, and there was this little bit of young oceanic stuff that maybe had a hard time subducting. We've seen this problem develop other places, and as the system kept coming in, it would get abandoned, and it would be captured by the Pacific plate. So this little fragment of young Furlong plate subducted just a little bit. The same thing is seen further south in California and all along the western margin of Baja. There's a lot of these little platelets that got captured then by the Pacific. So the question then becomes is, what role does this, what we call the Pioneer fragment, this little bit of subducted plate, does it still exist? If it does exist, what does it mean? And if we say, well, how do we image that? Well, this comes to our next thing is we can go back to the fact that we now can image the subsurface at high resolution because we have lots of earthquakes and lots of seismic stations. So this is work done with Harley Benz and with Antonio Villaseñor, and we've redone the tomography published a couple of years ago in Tectonics of the crustal structure in Northern California at a resolution of a few kilometers. So not this 50-kilometer block thing, but a 1 or 2 kilometer resolution. And we see a couple of things at shallow levels, say at 10 kilometers depth. It's like a geology map. Here's the geology, surface geology, the Franciscan, the Klamath terrain, the Great Valley. Here's the Franciscan, the Klamath terrain, the Great Valley. They show up, they're mapped quite well. But if we go down deeper, we see different things. We go down deeper, well, the Great Valley, which is a deep sedimentary basin at shallow levels, is underlain by this ultramafic, ultramafic body that very high density, very specific characteristics. The Franciscan crust, though, is quite thick through here. Remember, it thickens associated with the triple junction. And then we see these pieces of oceanic plate. The Gorda plate starting to subduct here. We're at 20 kilometers depth, so we're just clipping the top of it. But we also see this thing here, which is the Pioneer fragment. So it still exists. It's still around 25 million years after it formed. And it's still traveling right along underneath the western edge of North America. It sort of looks a little bit like a subducted slab, but it's traveling in the wrong direction. It's traveling parallel to the coast. It's not subducting beneath it. So we've sort of answered these three questions: why, where it is, why it forms, and its location. That pioneer fragment maybe plays a role. But we haven't necessarily solved the full problem. You know, we sort of can describe it, but we don't know why. So that's where I want to spend the rest of the thing talking about what are the tectonics associated with this. And what we'll see is that although we think of Northern California as being, oh, it's the Franciscan terrain, it is, but there's actually three distinct corridors of deformational corridors recorded in those rocks. Now, some of it may be feedback, but some of it we think is related to the larger scale plate tectonics. So, what do we see? Well, here I've defined the corridors. We have this thing I'm calling the Pioneer Corridor. That's the wake of this piece of the Pioneer Plate that's sort of moved along with the Pacific to the north. We have the MCC corridor. That's the slab window corridor. Because if the Pioneer fragment's there, there's no slab window. So the slab window is occurring east of the Pioneer fragment. So this is this region here. And then we have this interesting thing we're calling the Selenian corridor. That's the Selenian terrain, which is sort of up along the western margin of North America. If you go to Point Reyes, seashore, that's Selenian terrain, etc. And it is Sierra Nevada-like. It's a granitic type terrain, etc. And so we have these things. Now the Pioneer and the MCC are basically the Franciscan. Now, interestingly, and the back and forth is not 100% clear, but the Franciscan is divided up into belts that have sort of similar type, behavior, but also different metamorphic facies and things like that. And they tend to match up with these boundaries. Well, I mean, I've drawn that, but I haven't necessarily convinced you that the Pioneer corridor is really the Pioneer fragment. So we can zoom in on what the tomography shows us of this area here. The subduction slab ends here, subduction here, San Andreas down here. And if we zoom in, we see that the Pioneer fragment extends. This blue stuff is the high velocity oceanic crust, 7 kilometers per second. And we see that all of the earthquake activity in the newly developing faults form on the eastern margin of it. And so that's our argument that it's serving as the shear zone boundary on which this new plate boundary at depth forms. Once you form it, it's well established. It's going to have legs. It's going to last for a while. So we have these three corridors, the Selenian, the Pioneer, the MCC. Each of them behaves differently. Each of them has a different tectonic history. Some of them, the history is oldest in the north and youngest in the south, the Selenian. The MCC or the Pioneer is youngest in the north and oldest in the south. So there are fundamental geological differences in their history. And we want to sort of figure out what these things are. And now this brings us back to where we started with all of this, the heat flow, the thermal regime. Now, in the 1980s, 70s and 80s, the big debate in sort of active tectonics was, are faults weak or strong? Now, in 2025, an active debate is, are faults weak or strong? And so the argument was made, well, the San Andreas, is it weak or strong? Different people did different things. The Stanford group went out and looked at the stress orientations around it. The USGS, Art Lockenbrook and John Fass, measured heat flow all up and down the fault, arguing that if it were strong, it would generate a significant amount of frictional heating when there were earthquakes on it because of the stress heating effect. And so they made all these measurements. And interestingly, they came up with a sort of a null answer. There was no evidence of heating by the San Andreas Fault, but yet there was still a region of sort of warmer than normal heat flow. This was that same AGU meeting where George and I presented our tomography and model, and Bill Dickinson presented the slab window thing. And the first one to print was Lockenbrook and Sass, because they had this paper in revision. So they just added an extra section at the end. Oh, maybe there's a slab window. Maybe that's what's producing the heat flow. Well, let's let bygones be bygones. But they each of these regions. This would be the Pioneer, the MCC, the Selenian corridor. They do have quite different heat flow patterns, so we can look at those. And if I do that, we'll start with the Selenian. It's sort of the outlier. It's not really San Andreas related, although it's the thing that defines the northern San Andreas. But it is this terrain that came from the south. It comes up, and when it goes through the Santa Cruz Mountains, it actually gets overthrust to the west over top of the Pacific Plate. There's sort of a detachment beneath it. So it's being sort of overthrown onto that. And it goes through a lot of deformation going through the Santa Cruz Mountains. The Loma Prieta earthquake being a prime example of that. And there's been a lot of work done studying this. And a few years ago, Bob Anderson back in '94 did a nice study looking at arguing the erosion rates and all that were related. More recently, the Baden and Olvers a few years ago put out a thing where they've done a more detailed thermochronological and other studies. And what they found, was that, okay, the uplift could be explained by this going around the corner, but they did apatite helium ages, they did other things like that, and they found very young ages right through the corner here. We can model that effect thermally in terms of the uplift, erosion going around the corner, and we find that the heat flow, those green boxes, is basically matched by the same thermal history that produces the apparent ages that have been seen in the thermochronology. So it's a very localized little study, but the things work. Now, serendipity, whatever, I wake up this morning and they had an earthquake there this morning, about 1 a.m., right in this area of the uplift that we think that where the heat flow is higher. A magnitude 4.6, so a real earthquake, not one of these, piddly magnitude 1s or something. Something people felt. Got some people, maybe, I don't know. Did the people here get woken up by that? Not too far away. Your instruments go off. Who was on duty last night? Nothing. Well, 4.6. But it did, I'm sure, wake up the people in Moffett Field or in Berkeley. It was felt and everything, but it's a beautiful 8-kilometer depth thrust faulting event, high angle thrust faulting, slightly oblique, with the fault plane exactly oriented what you'd expect for this. And so this is an active system. This uplift, this deformation is ongoing. So let's move now over to the MCC corridor. That's pretty straightforward. That's the one we sort of understood the most 20 years ago. We had the data we used hasn't really changed. We have the crustal thickening. The tomography, though, just makes it very clear what the crustal thickening is. We can see where the plate boundary forms. Everything sort of fits together, although it's got complicated history. In the north, it's thickening, then it thins to the south. There's a lot of things going on, but they're the things that we sort of knew about. We can model those. And again, the heat flow are the green boxes. This is what the models produce. We've also looked at this in terms of the metamorphic facies that will then show up in details of the geophysics. And it's sort of a way of also to make bona fide crust out of the Franciscan. I mean, the Franciscan is a melange, marine, ferruginous, is a mess of things. But by the time you get to San Francisco, the deeper parts of it have characteristics of like bona fide continental crust, higher velocities, things like that. And that would be the thermal history that goes on through this thickening, thinning that it has experienced. But the last one I want to talk about is the Pioneer corridor. This is the one I think is most interesting. It's this narrow belt between the San Andreas Fault, sensu strictu, and the Selenian terrain. and the MCC. It's the thing that we think has been affected by having this piece, this sliver of oceanic plate slide by it subhorizontally. We see it very well in the tomography. If we look at a profile along here, this is Cape Mendocino, so we see slab here, that, and we see slab here, Pioneer fragment there. It stands out very clearly. But interestingly, if we zoom in on that area up in the north, there's this very rapid change in the red stuff. The red stuff is very low velocity sediments, sort of unconsolidated, loosely deposited sediments. And so that is the Eel River Basin. It's a deep basin. The seismic people say it's at least 4 or 5 kilometers thick, but the oil company people haven't gone deeper. We say it's about 10 kilometers thick based on the tomography, but over a distance of less than 10 kilometers, it is erased. That 10 kilometers of sediments, as the system moves through, gets uplifted and exhumed. Or at least that's what the picture looks like. Question is that really what's happening? I mean, it's true, that's 10 kilometers in a million years, that's 10 millimeters a year of exhumation. That makes us, I think, the winners for the fastest exhumation globally. Taiwan also ran with like 6, but in Taiwan, at least they have mountains. If you've been to Northern California, Cape Mendocino is nice and hilly and stuff, but no one would call it a mountain. There's no named mountains in California at Petrolia, California. So what's going on there? Well, we think we have a mechanism, the Eel River Basin being formed in advance of the migrating change in plate boundary because of some geometry effects on the slab. It's getting fed from the Eel River, which is just pulling huge amounts of sediments out of the coast ranges. It's very prolific, but also it's being fed by the stuff it's cannibalizing itself, right? The stuff that's being uplifted, much of that's just going back into it. And so we then re-expose the Franciscan Formation just south of it, and we geologically do that. But this short period of burial to 10 kilometers and then exhumation should have a thermal effect. So does it have a thermal effect? Well, the heat flow says it does. It just spikes right there. There's a short area of the highest heat flow in Northern California, 70 to 80 milliwatts per square meter. That's basin and range heat flow. That's the stuff, that isn't evidence of a subduction zone. Subduction zone, you go north of this and it's 35 milliwatts per square meter. Huge change. And then it decays as we go further to the south. We have the tomography, which says there's this huge amount. We also have sampled this now for low temperature thermochronometry. So we've got apatite helium and apatite fission track along a profile across this. We expect those to be reset, but not totally reset necessarily, because we're heating things up to like 70 degrees, not up to 150 degrees. So we've done those things. It ends up that the apatite fission track data behaves according to textbook. We model the partial annealing of it and all the track length distributions with the history that we show. And this is the model. These are the data. I mean, it's frighteningly good fit. I mean, we aren't trying to fit the data. We just have this model. The apatite helium's not quite so clean. The problem with apatite and helium and something like the Franciscan is those minerals have been through a lot. And there's a lot of these sort of partial retention issues and things like that. So the ages are a little weird. As we go to the point where we sampled the deepest in, then we do get the very young ages we'd expect. In between, it's like ages are all over the place, and there's been analysis for that. So just to finish up, we have these 3 terrains or 3 corridors. They've each had totally different tectonic histories, and we can follow them from San Francisco to Cape Mendocino just at different stages of maturity. The big question now is, what does this mean for the earthquake potential on all of these different major faults? That's still an open question. I have my opinions. Since there are people from the USGS in the room, I have to be careful not to, even retired, he's still, but the point is, this sort of difference, I mean, we have things that have quite different histories juxtaposed across major plate boundaries. So with that, I'll finish up, and thank you very much. Chris. It would be the Hayward through the Bay Area, right? Yeah. Right. I mean, I think that, in the simple mind I have, it seems to me that faults that sit above where the driver is, where the main shear zone is, should be the ones that are, in a sense, more driven. And so potentially could either have more activity or, if the time between them is longer or whatever. But there's nothing else between them and the driver. Things like the San Andreas, which has to be connected to the driver through some more complicated detachments or other things, its history may be more complicated, but it may also, a lot of the energy, I don't want to use the word energy, but a lot of those displacements can be absorbed in other places. But I do think this is why that fault system seems to develop pretty quickly. I mean, by the time you get just south of there, it's the real fault, and it's the only fault that's really active. Once you get south of Hollister, the other faults down there, Sur Nacimiento, things like that, are very inactive. But north of here, we now still have 3 or 4 major faults. And I think the ones, though, that are right below or right above the shear zone are going to be the ones that have the most likelihood of major events. Follow up on that. What are the Mm-hmm. So if we just look at, well, if you can't use the geodetic data very well because it's not recording much of the slip rate. It's telling us what the plate boundary shear rate is. But what you can look at is sort of paleoseismology, the actual offsets in trenches and stuff. And for all of those, if you negate 1906, the San Andreas is about 10 millimeters, 12 millimeters a year. The Hayward is about 10 or 12 millimeters a year. They're all in the same ballpark. So there doesn't seem to be sort of on the short-term geological, this is a few thousand years. There doesn't seem to be too much difference amongst them. On the longer term, we don't know. I mean, what we do know, though, is that if you look at the major sort of offsets of, say, the volcanic terrains in California, I mean, Bill Dickinson has pulled them back together. Those tend to be along that, what we would call the plate boundary. So, and that's, the 200 kilometers of offset between the pinnacles and the Sonoma volcanics or whatever it is. That is, again, on this, what we would call the main structure. So it's hard to put hard numbers on them. Okay, Chris. Yeah, there's a whole nother story there. Well, no, but I mean, I think it's an important one. It plays a big role in it. I had a talk I gave years ago about why is the San Andreas so creepy? But it's creepy in very specific places. From Hollister south, the main, what we call the San Andreas, is creepy. To the north, the main creeping sections are on the Hayward, are on the Rogers Creek, and on the Makima. And they all have major creeping sections. So I think it's, if you're right above where you're shearing every day at 40 millimeters a year, whatever process drives the creep, you're localizing it there. So the creeping history, I think, is related to that whole situation. The San Andreas itself, once you move away from Hollister to the north, it basically has no creep on it. Maybe a millimeter a year in spots.